While I wait to get started, let me just thank the committee for inviting me here today to talk at this workshop. It's been very interesting here listening to the talks this afternoon. Before I get started, though, with the technical part of my talk, which is going to be on solid-state quantum photonics, there's a few things I wanted to discuss. First and most important is that I've been fortunate to work with a group of fantastic students, postdocs. Without them, none of this work would have been possible. I've had fantastic colleagues at the University of Rochester and outside of the university, in particular Mishkat, who I see sitting over here. He and I have worked together on a project for the last 5 years, and it's been a lot of fun. I've been fortunate to have funding from a number of the funding agencies. Related to that, I have a few postdoc positions available. So if either you or you know somebody looking for a postdoc, please send them my way. The second bit I wanted to talk about is, I know I wasn't able to make the session last night on workforce development, unfortunately, but I did want to make you aware of a few activities we have ongoing at the University of Rochester related to that. First, this upcoming summer will be the 6th time that we've put on the Institute of Optics Photon Camp. This is a week-long immersive experience in optics for rising high school seniors. The idea is just to get them informed about optics and all of the career opportunities that are there for them. On the left there in this picture, that's our cohort from last year. The high school students turn up, they get paired off into teams, they work on week-long projects. Some of you might recognize Jaime Cardenas right here. He worked with a group of high school students last year on a project related to integrated photonics. The capstone of this experience is a poster session where their family and friends come on campus and learn about what they worked on during the week. Photon Camp also serves as a springboard for summer-long internships at the Institute. Last summer, I worked with 3 students, 2 of them pictured here from East High, and they were just there to be paid, which was important for them, but also to learn about optics and get them excited. The second thing we have ongoing this summer at the Institute is our Nanobio and Quantum Photonics REU program. This will be the 2nd summer that we've run this. Last year, in fact, we had a student that worked in my group from RIT, David Speaker. You will hear a little bit more about him later on in the talk. The third administrative thing I wanted to make this audience in particular aware about is this summer, at the beginning of August, please save these dates. We are putting on the 11th Coherence in Quantum Optics Conference at the University of Rochester. This was started in 1960 by Emil Wolf and Len Mandel. The last time we ran this conference in 2013, we had over 200 scientists attend. There are more than 160 papers. In the middle here are some of the colleagues from the University of Rochester, Joe Eberly in the middle, Nick Bigelow, and we were fortunate to have Serge Haroche, who won the Nobel Prize the year before this last conference, there to talk. The CECQO conference is an activity related to our Center for Coherence and Quantum Optics that we have on campus, and this is a multi-departmental effort where we think about and explore issues related to, as the center name says, coherence in quantum optics. Now, at the last, the 2013 CCQO conference, one of the main research themes, no surprise since I was involved in organizing it, was solid-state quantum optics. And so what solid-state quantum optics is, for those of you who are unfamiliar, basically what we're trying to do, or the scientific interest is we're taking the typical substrates people have used in quantum optics, something like an atom or an ion, and we're replacing it with a solid-state material. And we're particularly interested in understanding and controlling how light and the solid-state material interact. And the reason we want to study and understand and control this interaction, the sort of long-term vision of solid-state quantum optics, is that you can then make devices that elicit desirable macroscopic responses from structuring the nanoscale physics of the system. Now, the reason we explore this is solid-state quantum optics is a springboard for technological opportunities that are bringing us all together here today. In particular, one of the killer applications, I think, for solid-state quantum optics is integrated or on-chip quantum photonics. I'm sort of preaching to the choir if I point out the opportunities that are here. If you can get devices that work, there is things we could do in information processing. There's new approaches to sensing. There's a whole wide range of ways to generate interesting states of light, from single photon states to squeezed states to more exotic states of light. And the reason, in a nutshell, why we are interested in solid-state materials is that the hope is that we can leverage semiconductor fabrication infrastructure that is already available. There's an opportunity to scale up systems once we figure out the constituent components. It's neat that we're able to quantum engineer device resonances. That's what this picture is showing you right here. These are nanoscale quantum dots where just by changing the radius, the color of light they emit changes. This is kind of a vivid example of quantum engineering. And then the last point of why solid-state materials are interesting is it's possible that we can devise and design quantum hardware that could potentially also be robust and even deployable. Critical for quantum science based on solid-state materials is identifying efficient and stable, what I call quantum light solid-state matter interfaces, so light matter interfaces. The idea here is that you can connect the internal states of quantum emitters with states of quantum light. Typically, this takes the form of spins in your matter, and photons, single photons are your light. So to give you a bit of a flavor of what that looks like, I'm showing you here on the left is a TEM image of an indium arsenide quantum dot. The dark black is that indium arsenide. The things capping either side of this pancake-looking object is gallium arsenide. The length scale across here is 2 to 5 nanometers. And to make this work is a light matter interface. Critical is that we have a ground state that consists of a single spin. So imagine I load an electron into this quantum dot as its ground state. That spin is optically addressable, meaning I can shine photons on and drive transitions between these ground spin states and these excited excitonic states. And there's a variety of proposals that use this as the elemental currency to realize a variety of quantum information processing tasks. In the parlance of quantum optics, this up-down looking object is referred to as a lambda system because, of course, it looks like a lambda. Coming back to the science question, right? One thing that is critical to leveraging this kind of material for any quantum science task is being able to get light in and out, right? These quantum dots are buried between high index interfaces. So there's a point, not so much recently, but in the past when we were just focused a lot of attention on how do you efficiently get light in and get light out of these things. And it turns out there's a variety of ways that you can structure the photonic environment to enhance your ability to interface the light with the quantum dot. What I'm showing you here is just an example where we do a very simple experiment is I change the color of my laser beam that's illuminating this quantum dot, and I just sweep it across the quantum dot resonance. This very shallow curve you see here as I change my laser frequency represents the amount of light that is transmitted through this quantum dot. Now you see when the system becomes resonant with the laser, there's a very small amount of light transmitted. Now, by structuring the environment, we're able to enhance this coupling by over an order of magnitude. And outside of the fact that this is interesting, enhancing this interface, it also allowed us to do some technological things. So changing gears a little bit, there's a variety of quantum technologies that can be built on top of this light matter interface. So first, well, these quantum dots are a source of quantum light. They can emit single photons, they can emit correlated photon states, they can emit entangled photon states, they can emit squeezed photon states, they can emit almost any quantum state of light if you drive the thing the right way. The typical way that we test if a system is emitting single photons is a Hanbury, Brown, and Twiss interferometer. It's sort of simple to understand. You send a stream of light onto a beam splitter, you record a click, let's say on APD1, you wait a certain amount of time and record a click on APD2, you make a histogram of these clicks with respect to the delay between clicks, and you normalize it, and then the structure of that plot is a proxy, okay, for the photon number statistics, or the statistics of the photon number probability distribution of the light source that is illuminating your beam splitter. That's a mouthful. It's so obvious when this is a stream of single photons. One photon shows up to the beam splitter. If it transmits through, I get a click on my start detector because photons can't be split, right? These are indivisible objects. I will never get a click on my second one, right? So at 0 time delay, I should have 0 probability of getting a click in these two different spatial locations. The data, of course, bears that out. What you're looking at here is exactly that kind of measurement with the light that's been scattered off of my quantum dot. And as expected, at 0 time delay, this pronounced reduction in the signal, this so-called anti-bunching dip, is an indicator that the thing that is delivering me light is sending me a stream of single photons. I can change perspectives actually with this same light matter interface. I can ask, is it possible to use the ability to quantum engineer the resonances to do nanoscale sensing? The answer is yes. I can sense electric fields, I can sense magnetic fields. Here's an example where we do electric field sensing, and what we've built here is what we refer to as an all-optical electrometer. The idea, again, is very simple. I'm doing that experiment where I'm scanning my laser energy across my quantum dot optical transition. I can do that in let's call it a naked environment. I can do it in an environment where I load a single electron charge. In the presence of that charge, there is a stark shift on the electronic structure of my quantum dot, and so there's a shift in the resonance. I can use that shift to tell me something about the presence of an electron. It turns out that the sensitivity of this device, this optical device, is comparable to the state-of-the-art in radio frequency single electron transistors. All right, so here, this one device, it can generate quantum light. It could be used as a quantum sensor. It also could be used as a quantum memory. Now I need to rely on having more than one quantum dot in this case. So here what I've shown you is two adjacent quantum dots. There's arrows within the material indicating that I could prepare some state, and let's say the top quantum dot, I can control the coupling with the bottom quantum dot, potentially writing some kind of quantum information into this neighboring partner. This information can be stored. The second dot is like a memory. And then I can use the light that's scattered off of the top quantum dot to tell me about the state of the spin, in this case, in the bottom quantum dot. And so how you see that here is the up arrow and the down arrow correspond to the orientation of the spin in my quantum dot memory, and whether or not I have signal or I don't have signal is telling me about that spin's orientation. Now last but not least, okay, our quantum networks. Now we're not quite there yet with quantum dots, but we can get them into pairs. People are starting to put multiple quantum dots on a single chip and linking them on chip with photons. You can imagine also having a partner chip that has another array of quantum dots. As you start scaling up these chips, you're building up a quantum network, and you can dream about distributing entanglement. These are hard problems, but people are working on them right now. Now, quantum dots, of course, are not the only material for solid-state quantum optics. There's a whole wide range of materials. People, of course, study them for a variety of different reasons. Different materials have different attributes. I think there's probably an attitude that's emerged now that for quantum information science, it's going to be kind of stealing the good attributes of all of the materials and hybridizing them together to achieve particular tasks. But nevertheless, we have still continued to sort of, I guess what I wanted to say here is, in addition to materials that are optically active with photons, when I think of them, I tend to think of in the visible region of the spectrum. Of course, people are clever, and we've heard some of these talks earlier today. Even in lithographically defined materials, quantum optics is starting to emerge with microwave and radio frequency photons, and I think that's also particularly excited for solid-state quantum optics. Now, in talking about the materials, I want to also give a little perspective on quantum technology and innovation. So each one of those materials has gone through or is going through this kind of investigation or this kind of life cycle. So every material, there's some discovery. We identify there's a new quantum emitter. The spectroscopists get excited. They start studying this quantum emitter or this quantum system, learning about lifetimes and coherences. They start maybe interfacing it with other systems if they think that that could be beneficial. Slowly but surely, there are proof of principle demonstrations, and I started to show you some of these with the indium arsenide quantum dot. We can generate quantum states of light. We can do quantum sensing. And then they get to a phase in their life cycle where we start trying to make better devices and translate them to quantum technology. Okay, but the point I want to make here is quantum technology, for me, is not really quantum innovation. Okay, and I think that that's what they're after. And so what I'm going to share with you is something I learned from Duncan Moore. He's another colleague at the Institute of Optics, and he also runs our Technical Entrepreneurship and Management program. And so Duncan doesn't refer to this as this, but this is how I refer to it. What he told me is, he said, Nick, if you're going to have innovation, this is what he was telling me about, you need not only a great technology, but you need a market opportunity. So for us, what we need is a market opportunity and a quantum technology to have this quantum innovation. So I refer to this as Duncan Moore's law, so it's not confused with another Moore's law everybody probably knows about. But the reason I wanted to bring this up today and share this perspective is that what I think is great about this workshop is the participation not only of the researchers but also of industry. And I think industry's perspective on what market opportunities exist are going to be very important to driving quantum innovation. There's lots of different quantum technologies that we are all pursuing, but until we know what the best market opportunities are that are out there, it's really hard for us to have this quantum innovation. So I think these partnerships are going to be very fruitful as we move forward in the future. Now, coming back to the different materials, I've said a bit about quantum dots. That's kind of a little bit of an older material. What I mean by that, it's mature on that life cycle or that timeline I just showed you. We are also, of course, looking at other materials. We're particularly excited about these atomically thin semiconductors or metals or insulators that you can get. We broadly refer to these as two-dimensional van der Waals materials. The reason being we can also layer these in a variety of configurations. Some of the benefits of working with these materials is they're cheap, we can integrate them, they actually have different internal degrees of freedom besides the spin that could be useful for information processing, and we're exploring that. Now, there is a whole suite of these 2D materials, so there's lots of opportunities as you explore this palette to not only do quantum optics, but to potentially have impact in quantum photonics. Now, instead of boring you with the details of the spectroscopy of these materials, I thought it made more sense to show you an application where we actually use the quantum light from one of these materials, or we put this quantum light to work to actually do something. So we have a little widget, it's generating us our quantum state of light, and we use this to do something that I think is interesting, maybe not the most practical thing, but is interesting nonetheless. And so what we have done is we've looked at I guess I would say a foundational problem in quantum mechanics. And what this problem is related to this dual identity of quantum objects. All right, so quantum objects, if you remember back to your first quantum mechanics course, sometimes behave like waves, sometimes behave like particles. Oh, so everybody's seeing that now, not just me. There we go. All right, and so so as I was saying, you remember freshman quantum mechanics, particles or quantum objects sometimes behave like particles, sometimes behave like waves. We refer to this as duality. Niels Bohr came on the scene. He tried to give some qualitative explanation of this duality. This gave rise to his complementarity principle. If you look through enough of the stuff that Niels Bohr has written, what you distill out of it is the following comment. You have some physical system. It admits multiple descriptions. These descriptions should be both exhaustive in how they describe the system, and they should be complete, okay? And so the question is, can you test this? And so again, we took our single photon source, our quantum widget, and we built the canonical interferometer to test both classical and quantum interference, a Young's 2 pinhole. Of course, there's nothing new under the sun. This issue about quantifying complementarity is now probably about 30 years old. The first paper by Wouters back in 1979, and this has been visited many, many times since then. And what all of these papers, in one way or another, they come up with a way that you can distinguish the paths that your quantum object takes to your detector. This somehow captures the particle property of this quantum object, and there's a measure for that related to the probability that a photon passes through slit 1 or the probability that a photon passes through slit 2. If it happens to pass completely through slit 1, of course, on my detector I see no interference. Now, I cannot look at either path, and I can let both paths engage my detector. And when I do that, I'll find an interference signal. The depth of the visibility, which is nothing more than the probability at a maximum minus the probability at the minimum over their sum, all right, is a measure of how wavy this quantum object is. This gets brought together in the following inequality. My measure for particleness, d, and my measure for waviness are both squared and added, and they're always found to be less than or equal to 1. This is a problem I actually ask in my wave optics class that I teach the undergrads in the institute. We said the waviness somehow is the visibility of our interferogram is somehow a proxy for waviness, and in the technical jargon, it's a measure of the spatial coherence between our two pinholes. If I simply change the polarization orientation at these pinholes, I've done nothing to change the coherence of this wave, classical or quantum, but the visibility goes away, right? My signal becomes flat again. So we get this peculiar situation where I have signal, in this case single photons falling onto my detector. They're not distinguishable. The visibility is 0, but I know light. I'm getting clicks on my detector. So if we look back at what Bohr said, we actually realize we violated both, or we're violating both of his observations in describing complementarity. The first thing is that it's clear if V and D are both 0, that the way we're describing the system is not complete. Something is missing. The second bit here is related to the fact that the distinguishability and the visibility don't always equal 1, but they always equal the degree of polarization of the system. All right? So there's this polarization coherence theorem that we discovered. And so what does that mean? It means that they're not mutually exclusive, right? They don't trade off with one another with respect to 1. They trade off with one another with respect to the degree of polarization. And so you can appreciate what's going on here if you look at the state of the photon that's arriving at my detector. You'll notice here, as I've written it out, it's a state that brings together two different paths with two potentially orthogonal polarizations. And since I can't factorize apart this path and polarization information in the photon, it's entangled. And we know how to measure entanglement. We can use the concurrence in this case for our single photon. There's a relationship that I won't say too much about, but the relationship is the polarization, degree of polarization squared and concurrence squared is equal to unity. Knowing our polarization coherence theorem and knowing about the concurrence, you can change that inequality that we started with to an equality, where it now has an element that captures the degree of distinguishability, an element that captures the waviness of our quantum object, and an element that captures the entanglement between our object's degrees of freedom. Now, I said we were doing this in the lab. This is actual data where we have generated a variety of single photon states with our quantum source and experimentally verified this upgraded complementarity relationship. So what we say, in the lab at least, is somehow Bohr's complementarity wasn't complete, and it wasn't complete because he didn't recognize entanglement was an important feature of every quantum object. When you recognize entanglement is important, this kind of, that original inequality between the visibility and distinguishability is upgraded to an exact equality that we're showing you here. Now I said David, who is in our RU program, okay, was going to come back later in the talk, and this is where he comes back. He was, during the last summer, the V guy in this paper, meaning he was measuring the visibilities of these single photon interference experiments. He's a co-author in the paper that we're just getting ready to submit. I did want to change gears. I know we have just a few minutes left. I know we're talking about quantum photonics, but I think a really important and emerging area that's going to be important in integrated quantum photonics is quantum phononics. I don't know if anyone has mentioned that yet. I know Mishkat talked a bit about this yesterday, and I think there's lots of opportunities to think about not only phonons in macroscopic materials and generating quantum states of phonons. How would you prepare them? How would you measure them? How could you use them to control other things? But I also think in this kind of emerging area of optomechanics that Mishkat and I work on, levitated optomechanics, there's also lots of opportunities for quantum photonics. I think Mishkat yesterday showed you some images like this. So what we're working on is optical tweezers in vacuum. These systems are kind of cool because you have mechanical resonators that are untethered from any kind of substrate, and that means they can have pretty gigantic quality factors. They're also literally kind of cool because we can control the trap that acts like a glove for these levitated particles, and we're able to suck energy out of it, cooling down the mechanical resonator. The mechanical resonator is the center of mass motion of this trapped particle. The data here on the right is just a position spectral density of one of these oscillation directions. This is when the system is initially trapped. Everything is at room temperature. We start feeding back on the system the right way. We're able to suck energy out. And you see that by this change in structure of the position spectral density of this mechanical oscillator that we're measuring. Now, our group isn't quite there yet, but there are groups that are already preparing phonon number states that have about 10 phonons in one of these oscillation modes. We're a few orders of magnitude away from that right now. But we can still consider phonon states. Right? We might not be looking at number states right now, but what we are looking at is coherent states of these phonons. And what we're particularly interested in is pushing and pulling on this system in just the right way so we can generate sustained mechanical oscillation. And I think Mishkat, I'm pretty certain, spoke to you about this yesterday. Here is just an illustration of our experiment. We're levitating one of these nanoparticles below threshold, and above threshold there's a characteristic change in how the nanoparticle explores the focal region of our optical trap. We can construct phase space plots, both below threshold and above threshold, seeing the changeover from thermal to coherent states. I'll let you figure out which one is the data and which one is the experiment between, or the data and the theory between these two plots, because I think the overlap is kind of great in this particular figure. So I know you heard about that yesterday. What I wanted to just flash a slide or two more on is related to quantum metrology with phonon lasers, right? Lasers are great for metrology. It seems like we should be able to use this same kind of system to do metrology. So what we started doing in our lab is we're illuminating this whole optical trapping apparatus with a second laser that we can control how it pushes and pulls on this nanoparticle. So there's an extra force in the system that we can measure. And what we're doing is an injection locking experiment where we're able to change the frequency of how we push and pull with this second laser so that we can sweep it across the phonon laser frequency. When the two frequencies get close enough, there's a locking that occurs, and so these unrelated phases of our applied force and our phonon laser become locked to one another. All right, when this locking happens, the range over which we observe this can then be related to the amount of force that we're pushing and pulling on the system with. Now, not going into the details of how we exactly do this, but the locking range of this plot on the right gives us information directly about the force that we're applying. And in this particular example, we're measuring an optical force of around 30 attonewtons. This hasn't been optimized at all. These are some of the first data sets, but I think there's real opportunities for this system in quantum metrology. So with that, I appreciate everybody's attention. I see Ed is getting ready to run me off the stage. I figured I waited 10 minutes, so I can steal 2 more minutes. If you have any questions, please feel free to ask. Thanks.
Excuse me.
We have time for a couple questions for Dr. Vamivakas. Yes, sir. I think that was a microphone.
Is this yours?
Yeah, that was mine. Did I do that? When the screen flopped? Someone else did that, yeah?
With the quantum dots and some of these defects in dopant systems, one often worries about the fact that it's very difficult to get 2 of them that are the same. Could you comment a bit on that and what the possibilities for that is and how it affects their use?
Yeah, no, I think that's obviously it's a great question. There is challenges with the indium arsenide quantum dots to getting them all to have the same transition energies, but there's ways that you can engineer that with that particular system via strain, via application of static electric fields across the dots. Now, have people figured out how to do this with a large array of them? Not yet, but there's still a material science challenge there. Now, with some of the other systems, the 2D materials, again, strain is a big component of determining exactly the optical transition energies, and we're doing some work with pillar arrays that allows us to engineer that strain to make transitions more commensurate. So you'll notice the data stopped as the array started getting bigger. There was no more data, there was just illustrations, and that's for a reason.
I think we have a question up in the back.
I'm just wondering if you can say anything more, any details about the light source in your complementarity experiment, the wavelength and repetition rate, or just anything at all about it.
It's top secret. I can't divulge that. No, so the light source, it was a defect in hexagonal boron nitride. The emission wavelength was around 780 nanometers. We were just driving that system with a continuous wave laser and collecting the photons that were coming out of it.
Any other questions?